So I'd like to go over notation that's in the class, all of the classes we do through calc and linear and difference equations. Some of it's set notation, some of it's just basic notation, just so we're all on the same page in case you haven't seen it before. So first, let's look at some set notation. So I'm sure you've seen sets and set notation before, but let's talk about the different kinds. There's interval notation for real numbers. There's set builder, some other symbols, things like that. So first, let's take a look at what's called set builder. So set builder notation would say something like this. So you'd say the set, so that's that symbol for a set, and you can say a number, x, or something, such that, so the vertical bar is such that, and then what comes next needs to be true, such that x is less than or equal to 2, for example. In interval notation, which most books do up till calculus, it would be like this. It'd be parenthesis, negative infinity, or right, approaching negative infinity to the left, and you go up to 2, and then you would put a bracket to include 2. Okay, and that's read the set x such that x is less than or equal to 2. So you can see that is quite long compared to this statement or even this one. So often the set builder is very useful, or you could use the interval. So we'll be using basically all of it. Then you have some special types of real numbers. So we're looking at the number line, right? So you have the number line, and we consider the number line all the real numbers. Okay, so you start at 0 here, and then the interval we just talked about here, of course, is from 2, and let me change colors here. So you're going from from say 2, which would be here, and then this is going to the left. So this is going this direction. Okay, so that's how you graph it, of course. So we want to classify the different real numbers. So we want to classify basically different types and what they're called, just so we all know what they are. So natural numbers look like this. Sometimes the n is on the diagonal, or the double line's on the diagonal, but it's easier to write it vertical like that. Naturals are what you naturally start doing. It's basically 1, 2, 3, etc., 4, 5, 6. Those are naturals. I'll say natural numbers. Then you can throw in 0, and those are considered the whole numbers. 0, 1, 2, 3, etc. Those are the wholes, or whole numbers. And we often don't say naturals or whole numbers. We use integers. Let me keep that down for a little bit. Okay, so integers is the symbol z, like that. And you throw in the negatives. So usually we classify the integers. You say positive integers or non-negative integers, that kind of thing. So you say dot, dot, dot. And it would be like -2, -1, 0, 1, 2, etc. So we can write it out like that. And those are the integers. So when we talk about naturals, instead of saying naturals, sometimes you'll just say positive integers. So it's not 0, right? 0 is not positive. So positive integers would be the naturals. Non-negative would be the wholes. All right, so non-negative is the whole numbers. Positive integers is, did I say that right? Non-negative integers are the whole numbers. Positive integers are the natural numbers. That's usually how you classify it, or you see it in books. Then when you get to fractions, you need to use set builder notation. So let me show you this briefly. So when you talk about integers, you can say what's the first one and the next one, or even going to the left. You know what the next integer is. It jumps like that. But when you look at, say, fractions, and let's just start at, so those are some holes here. Let's just start at, say, 0. So what's the next rational number? And of course, many of you know there isn't one. No matter what number you pick, let's say you pick this one, and we'll call that, say, I don't know, 1/5. Well, all you have to do is add these two up and divide, and you're going to get 1 halfway between it. So between any two numbers, there exists another number. And another, just another number. You can classify that as well. But it is true for what we call rational numbers as well. So I'm not going to get too much into that, but the rational numbers are basically the fractions. So at least that's how I like to show them. It's symboled for Q like for quotient. And so it's P over Q such that P and Q are integers. And we have to say one more thing, because what about this denominator here? What do we have to say there? We have to stipulate that Q does not equal what? Of course, 0 can't be 0. Can't divide by 0 ever. So we don't want to write all this out. We need some symbols for that, because we do this all the time. So the symbols we're going to say is this. So I want to say basically that P and Q are integers. So I can say I use this symbol for element of. So this symbol means element of. So we say P is an element of Z. Basically, P, it's basically just a nice way of saying P is defined to be an integer, or P is an integer. So technically, you're saying P is an element of the set of integers. And I won't write that out, don't need to. But this is a statement, meaning it's a sentence that's either true or false, or you're stipulating that it has to be true. Okay, these are rationals. Rational numbers. Okay, so then let's go into irrational. So irrationals, basically, it literally means what? Like not rational. Or you can think of it as cannot be written as a fraction. That's one way to think of it. So I'm just going to give you examples of these that are not rational. So, for example, and by the way, for example is e.g., means for example. I'll use that later. So numbers like pi, e, those are irrational, and those are actually called transcendental. They're different classification. Then you have the square root of, say, 2 or the fifth root of 7. Those are all irrational. These are actually irrational, but they're not transcendental because they're basically solutions of roots of polynomials. Again, won't get into that so much, but then you can talk about more like trig functions, like sine of, say, 1. That is irrational and also transcendental. Don't worry about that. I just saying what they are. They're irrational. But it is a field of study if you want to get into that. let's see. And so if you put these two together, the rational and not rational, that makes up all the real numbers. So the real numbers is symbols with an R, and we often use, or you could do the interval notation like this. And those are real numbers. Okay, so number line, you just basically say, if this is, say, 0, you're going the whole length of that. Put a double line in there. So you're going from negative infinity and then finish the whole number line. Talk about a little bit about complex numbers. So complex numbers look like this. Complex numbers use this symbol, the I, as a square root. So complex, we know, is the form a plus bi, such that, so if you're in calc, you would have seen this in algebra. So if this is algebra students, you may not have seen this yet. You would have in like high school algebra, but it kind of depends. So again, quick review. It's the form a plus bi such that a, b are real, and I is defined to be the square root of -1. And there's other definitions of how you say that, but those are complex. You could talk about the complex plane, things like that. I don't want to get into that now, but you can look up that stuff, complex plane stuff. There's a whole field of study, of course, on what's called complex analysis that uses much of this stuff in the complex plane. Okay, so those are all the sets and notation that we'll be using. There's more, but we'll define it as we go. I just want to make sure we're on the same page for much of this as we go here. Let's do a couple things about sets in the notation. So here's an example. So if I say, for example, 4 is an element of the set -2 to 5, is that true or false? So that's a statement. When I say that's not like just a thing, it's a statement. You read it as 4 is an element of the set, including -2 to 5. That would take up an entire line. So there's a lot of information in math. It's just, that tells you a lot. So is it true or false? This is, of course, true. 4 is in that set. Then if I said something like 3 is an element of 4 to 8, that, of course, is false. That's a false statement. All right, so moving on. Some more notation we will use. So this is notation for kind of logic type stuff. Upside down A means for all. So if you write that, that means for all or for every. Backwards E, capital E, like that, means there exists. So there exists a number such that so the existence of something. This symbol is like the reverse of that. That means such that. We use that a lot. So like you'll say something, blah, 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 where the next thing follows. So you use the symbol such that, and it simplifies it quite a bit. Sometimes you'll see me use ST. I prefer to go ahead and use this. This is what I'm used to for when you get to higher levels, you use that symbol all the time for such that. And then, well, just to clarify, in the set notation like this vertical line means such that. You would not put this symbol here. Okay, so usually you use this vertical line, or you could use maybe 2 dots is sometimes done. But that's usually how set builder's done. So this is in a sentence form to simplify. Couple more. I already said the EG, but EG means for example. So I'll maybe define something and then say, for example, and then give you an example of whatever. And then the next one, often I'll just say, let's do like an example or a problem. Just the way it kind of flows a bit. And then the IE, that means that is. So that's for example. IE is that is. Sometimes we'll use that. It's not so much a math thing, but well, neither is the EG, but we use it a lot. So let's see. What did I forget? All right, so this is all the same meaning. I don't have my yellow there. Yellow works. So all the same meaning. So if I say negative infinity less than t less than infinity, t is an element of the reals. Okay, that's the same thing. And then the next case, if I say t is an element of 0, infinity, that's like positive reals. So that's uses this symbol, or plus, like that. You could actually put in 0 if you wanted to for whole numbers. So if you wanted, so this is a way to write whole numbers. You union with r plus. I don't really do that, but this is basically whole numbers. So see why that would work. Because positive reals, not whole numbers, I'm sorry. What am I thinking? That I meant to say non-negatives. This is non-negatives. Non-negative real. That's what I was thinking of. So non-negatives, that throws out everything that's negative, but includes 0. So that's different than r plus. R plus means positive reals. So this is positive reals. Okay. Some abbreviations I'll use. So solutions. I'll use the abbreviation SOL and then the N with a line under it. And then if I put S, it means plural or solution or solutions. So it's like the the TIONS is the N, and you're leaving out the U for the vowel as well. And then equations. So equations, same thing, EQ, and you leave out the vowel, and then you put in the N with a line. So I'll use those abbreviations quite a bit. Let's see. Some Greek letters we're going to use a lot in, well, not all my classes, but especially in the Calc and Calc 3. So Greek letters. So often used in math. Okay, so many of these I'm sure you've seen them, but just to clarify or review, delta, that's uppercase, and then lowercase delta. Of course, pi. Epsilon looks like that. Theta. Phi. What else? Mu. Uppercase sigma and lowercase sigma. So upper and lower sigma, alpha, beta, gamma, alpha, beta, gamma. Those are the first three letters of the Greek alphabet, by the way, alpha, beta, gamma. There's more, of course, but those are the ones we use that are going to come up. Notice that this symbol is different than the such that symbol here, or the element of. So that's not element of, that's epsilon. So I think that covers pretty much what I need you to have right away. We'll define things as we go, or different classes might need some other notation, of course, but those are the ones we use a lot. I want to make sure we're on the same page. This is good for basically all my courses. I teach algebra through differential equations and linear algebra. Okay, so just be familiar. I'm not going to test you on this in particular. I'm just going to be using it as I go. And you can always reference back to this or the video or the notes if you need to.